Okay, hello everyone. This is CIE Examinations Further Mathematics. It's 9-2-3-1-11, May-June 2014. Okay, and we'll move on to the first question without further ado. So the equation x cubed plus px plus q equals 0, where p and q are constants, q isn't equal to 0, it has one root which is the reciprocal of another root, and it wants you to show that p plus q squared is 1, okay? And how we're going to go about this is by writing, observing that we could factor this equation. Let's imagine we already knew the roots and just call them, we'll just call them a, b, and c. So x minus a, x minus b, x minus c equals 0. So we could write this equation in that form, and we know that one of the roots is the reciprocal of the other, so we can just say straight away that c is 1 over b, perhaps, without any loss of generality. We can choose any one. So that implies that we have x minus a, x minus b, and then x minus 1 over b equals 0. Okay, so that's pretty much all the information we're given in the question. Now we have to figure stuff out. The first thing to observe is that where this q comes from, q is the product of these three roots, because that's the only term that doesn't have an x in it when you actually expand this out. So if we want to figure out what that is, q equals minus a times minus b times minus 1 over b. So the minus b and the minus 1 over b is just going to give you 1. So we get q is a and that's the first thing to observe. The next thing to observe is that there's no x squared term. So where the x squared term comes from is that we'll get maybe this x times this minus c. So we'll get a minus c. Oh, whoops. Minus c. And then we'll get from the minus a times x, we'll get a plus a inside the bracket, so the minus is that side here. We'll also get the same for b. And this is the x squared term, but seeing as there isn't an x squared term in this equation down here, we know that that actually equals 0. And from that gives us that q plus b plus 1 over b equals 0. So q is minus b minus 1 over b. And then if we look at all the terms in front of the x, that's when you get two of the roots multiplied together. So we could have a times b times x, that'll be one of the terms. So we're going to get an ab plus an ac, so every pairwise way of multiplying those three together. So ab, ac, we're missing one, cb, bc. That should equal p. Okay, but we already know that BC is 1. AC is Q over B, and BA is QB. Okay, and so we can now use, we already know what B, we can factor out a Q here because we already know what B plus 1 over B is, that's minus Q, and then using that information that should give you this P plus Q squared equals 1 straight away. Okay, so the basic idea is just, you imagine you've already factored it out into this, and then you try and find out what each of the terms is. So you find out the x cubed terms just by multiplying all the x's together, the x squared terms are just 2 x's multiplied by a root, and then you do that, and then once you look at all the coefficients, you can then pretty easily prove that p plus q squared equals 1. Okay? Right, for the next one, expand and simplify this. Well, that's pretty simple if you just remember binomial expansion. So if you remember how to expand r plus 1 to the 4, I'm going to write this out because it's useful for the next part of the question. You get an r to the 4, obviously, plus a 4r cubed plus 4r squared. Sorry, plus a 6, that should be a 6r squared. If you forget these, you can either use your calculator to figure out the n choose r values, or you can just write out Pascal's triangle. That's a pretty easy way of remembering them. 4r plus 1. And so if you take away an r after the 4 away from that, you're just left with these last 4 terms. So these ones are the answers. Okay, and it turns out that this is actually extremely useful for the next part of the question. So the next part of the question, they want to use the method of differences together with the results for these two. So you're only allowed to use these two. These are in your formula booklets. So this one is it's a half n times n plus 1. Okay, and this one is a sixth n times n plus 1 times 2n plus 1. Okay, so you're only allowed to use those two. The third one is actually in the formula booklet, but it doesn't really help us now. And the way we're going to do this is by observing that this r plus 1 to the 4 minus r to the 4, that equals 4r cubed plus 6r squared plus 4r plus 1. Okay, like as in the first part of the question. And what we're going to actually do is sum both sides. So it might not be obvious why we do that at the start. Obviously on the right hand side, this r cubed thing is the thing we're going to want to figure out. So we're going to end up solving for this. We know what the sum of r squared is because we're allowed to use that. We know what the sum of 4r is. We're allowed to use that. The sum of 1 from r equals 1 to n is n. So don't write a 1 here when you actually figure out the sum on both sides. Everyone always forgets that, but that will turn into an n. But on the left hand side, it actually turns out to be quite simple. because if you think about what this looks like, when we have r equals 1, we'll have 1 plus 1, which is 2 to the 4, plus a 1. And then we're then going to add that to, when r equals 2, that'll be added on to, that'll be a minus 2 to the 4. Whoops. It'll be minus 2 to the 4. And then from the other one, there will be a 3 to the 4. Okay, but this minus 2 to the 4 cancels with the 2 to the 4 from the previous term. And it's going to keep happening all the way through. So the only terms we're actually going to get left with on the left-hand side are going to be a 1, the first one, and then the n plus 1 to the 4, which is the very, very last term. Okay, so that's what happens when you sum the left-hand side. And then on the right-hand side, we have 4 times the sum of r cubed plus, well, the sum of 6r squared is 6 times the sum of r squared. R squared plus 4 times the sum of r plus n. Okay, don't forget this n, it's not a 1. When you sum 1 n times, you get an n. Okay, and if you just work through this, using the results we're allowed to use, some fairly simple algebra should give you this, which quite weirdly is actually the sum of r squared. Don't know if you noticed that. It's not part of the question. But look, there's a when you square a half, you get a quarter. When you square any n squared, obviously n plus 1 squared is n plus 1 squared. Okay, cool. So that's that question. Right, now this question is a question by mathematical induction. So we need to show that this thing here, for any value of n, is divisible by 24. Okay, so as with all induction questions, the first thing we do is we check the lowest case that works. So it says all non-negative integers. so why not start with 0? We could start with 1. Actually, not quite sure. In the mark scheme, I think they start with 0, but I don't know if you can quite, characterize 0 as an integer. But it does work when n equals 0, so we'll start with that. And the proof still works. In fact, it's even stronger if you start with n equals 0, because you have one more number. So check the n equals 0 case. We have 11 to the power of 0, which is just 1. 25 to the power of 0, which is just 1, plus 22, that is 24. So it's obviously divisible by 24. So the n equals 0 case works. Right, now the next stage is always assume that the n equals k, so k is just some random number. We assume that n equals k is true. Okay, that's the next step in induction. And then the step after that is to consider n equals k plus 1. Okay, so first thing we do is check n equals 0 works, which it does. Then we assume that n equals k is true. And we're going to see that n equals k being true, does that imply n equals k plus 1 being true? Okay, so let's just consider what happens when you make this n a k plus 1. So we get 2k plus 2 in the exponent here, plus 25k plus 1 plus 22. Okay, well, 11 to the power of 2k plus 2 is the same as 11 squared times 11 to the 2k. So we've got 11 squared, which is 121, times 11 to the power of 2k, plus this plus 1 is the same as the 25. This is just rewriting in a different way. 25 times 25k plus 22. Okay, so that is what 11 to the that is what happens when you put in n equals k plus 1. Now let's see if we can write this in a form that makes it look like it's divisible by 24. Okay, and let's just observe that 121 is 120 plus 1, groundbreaking, and 25 is 24 plus 1. Okay, and the reason why we've done this is because 120 and 24 are both numbers that are divisible by 24. So 120 plus 1 times 11 to the 2k plus 24 plus 1, 25k plus 22. Okay, so if we just move down a little bit here, we can see that this is exactly the same as 120 to the 11 to the 2k plus 24 times 25 to the k plus, and then the bit that's left over is I'm going to put this in brackets. It doesn't really mean anything in maths, so don't write this in an exam, but the bit that we have left over, just kind of running out of space, is the bit that we would have had for when n equals k. So the bit we have left over is what I'm writing down now. That's the bit we have left over. And this bit is evidently divisible by 24, because 120 is, and 24, they're both divisible by 4, 24 even. And now, if the n equals k1 was true, which is what we assumed, then that would make this whole thing divisible by 24. So what we've shown now is that n equals 0 gives something that's divisible by 24, assuming that one number gives us something that's divisible by 24, implies that the next number also makes it divisible by 24, and that is the proof by mathematical induction. So that means that 0 implies that 1 is divisible by 24 when you put 1 in here, then that implies that 2 is, and then that implies that 3 is, because of this process we've just done. So the whole thing is proved by mathematical induction. Okay? Right, now for the next one. Obtain the general solution of this differential equation. Okay, don't actually have much space to work with here. Let me just see if I've got some more. No, I don't really want to go down and use that. So yeah, I'll just work here. It's fine. Okay, so whenever you're given a differential equation like this, it's a second order differential equation. At this level, we know that they're not going to be that hard. You can always make the same guess. And the guess that we can make for the solution is that x equals e to the lambda t. or you might have seen this lambda being an n before, okay? And if we put this guess into the equation, as I'm sure you've already seen many times before, we'll get a lambda squared minus a 6 lambda plus a 25 e to the lambda t. Sorry, one thing I forgot to mention is that when we're given a differential equation like this, first we want to solve the complementary equation, it's called, when this whole thing equals 0, so not when it equals 195 sine 2t. And when we do that, that actually gives us the most general solution. We could solve this straight away just by looking at it, inspection, which is what we'll do in the second part, but that won't give us the most general solution because there are some there are some functions when you put them in this equation that will give you 0 out that we would have missed otherwise. Okay, so yes, as I say, we put in this guess and we see that we get this is what we would get out, equals 0. And seeing as we know that e to the lambda t isn't equal to 0, we just have to solve this quadratic equation, which gives us a value of lambda equals, it gives us two values actually. I think it's lambda equals 3 plus or minus 4i. Okay, and when we put that back into our guess here, we see that we get x equals e, well, we can bring out a factor of e to the 3t, like so, and then we'll have an e to the plus 4it, and then an e to the minus 4it. Okay, so we know by Moivre's theorem that anything e to the I something, we can write that as a cosine term plus a sine term. Okay, so we actually know that we can get rid of the imaginary numbers and just write the solution in some form of some cosine function with some coefficient we don't know, or it could be anything even, with 40 plus some sine term, sine 40. And I know what you're thinking, shouldn't there be an imaginary number next to the sine term? Well, no, this b is completely general, so it actually absorbs that I term. This b can be anything. This could be imaginary, the a could be imaginary, but we're just saying we don't know, we're just saying some coefficient in front of the sine 40 and the cos 40, okay? So that's the general solution. How do we find the specific solution, the particular integral? Well, we have a sine 2t here, okay? So we know it's going to have to sine, and we have an x here, okay? So this is just the solution multiplied by a constant equals a sine 2t term. So we know that it's going to have a sine 2t in it, but we don't know what the coefficient is going to be. So we'll call it a d. Let's call it alpha sine t. Okay, but we also have a derivative in here of the sine t. So just to recap, we know it must be a sine 2t in here somewhere because this is just a multiple of the function equaling sine 2t. So they have to have a sine 2t on both sides, a sine 2t term, otherwise this can't be true for all values of t. So that's why there has to be a sine 2t in here. But if there is one in here, then when we differentiate it, we're going to get a cos 2 t term, which doesn't have anything to cancel with. So we actually also need a cos 2t term just to cancel with the derivative of the sine 2t term. And then we have a second derivative term, but that's fine because the derivative of, there will still be sine 2t's floating about because when you differentiate it twice, it'll get back to the same value, okay? So all you do is try this solution. You plug it in here, and you want to try and equate coefficients of sine 2t and cos 2t. When you actually do that, I think you get alpha equals 7, and you get beta equals 4, okay? That's what happens when you plug that in there, okay? Right. Now for the next one, I'll just, no, I think we can read that. Okay, so curve C has a polar equation a times 1 plus sine theta, where a is a positive constant and theta ranges between 0 and 2 pi, including 0, not including 2 pi. Okay, and once you draw a sketch. Well, the easiest way to start with basically all sketches, I'll do it down here. So we're going to draw it in the plane. So this is the x-axis, the y-axis. We'll say theta's going round this way. Okay, just to remind you, and r is away from the origin. in polar coordinates. And the easiest way to sketch things is always to think about specific values. So we'll start with here along the x line in this direction, and we'll think about when theta equals 0. So when theta equals 0, sine theta equals 0, so we just have an a. Okay, so let's say it goes through here, and it's at an a. So it's 0a, okay? And then by the time we go around 90 degrees, sine theta is 1, so this is actually 2a, so the r value is 2a, so it's twice as far away from the origin. Okay, and then we go to 180, sine theta becomes 0 again, so it goes through here at a, so 2a. So a, 2a, a. Then when theta is 270 degrees, we know it equals minus 1. So this whole thing becomes 0, so it goes through the origin here. Okay, now if we just join up all those curves, we know that it's going to be smoothly joined up. It's going to be symmetric about the axis just because of the way a sine curve looks. So that the sine curve, its behavior over the axis is completely symmetric. So we can just smoothly join all these like that, and that's what it looks like. It looks a bit like a heart. I think it's called a cartoroid or something like that. It's something that's shape. That's a special math shape. Looks a bit like an upside down heart. Okay, cool. So that's what it looks like. Now we need to find the exact value of the area of the region closed by C and the half lines. Theta equals pi over 3 and theta equals 2 pi over 3. Okay, pi over 3 is 180 over 3, so it's about 60 degrees. Well, it's exactly 60 degrees. So it's the region upwards of this cone. Okay, I want to shade it in. Actually, maybe I can shade it in a bit. This is going to look gross because it's green. It's very Christmassy. So it's these this area. Yeah, okay, that's the area we want to figure out. Okay, how are we going to do that? Well, just do a bit of revision of your regular maths. So you know that an arc area is given by 1/2 r squared theta. So an infinitesimal arc area, dA, will be given by 1/2 r squared d theta, okay? So we just need to integrate this. So if we integrate, find the area as 1/2 the integral between our two limits. So I'm not going to draw them in, but you know there's a pi over 3 and there's 2 pi over 3 up here, otherwise it can get really messy. R squared, which we've been given, it's a squared 1 plus sine theta squared d theta. Okay, so that's all you have to integrate. The way to do that is you want to expand this out, so you get a 1 plus 2 sine theta plus cos squared theta. You can then rewrite cos squared theta in terms of cos 2 theta. Actually, sorry, you get a 1 plus 2 sine theta sine squared theta. You can rewrite the sine squared theta in terms of cos 2 theta. You can integrate the 2 sine theta pretty normally. It should give you an answer of, I think, 4/3. Let me just double check. Can't see my answers. Oh no, sorry, it doesn't give you anything near 4/3. It gives you quite a gross answer. Let me write it down here. It's a squared outside of pi over 4 minus 1 minus square root of 3 over 8. Okay, that's what the answer comes out when you do this integral. Cool. Right, next question. The linear transform T of this is represented by the matrix M. Okay, actually you don't need to know that. Just need to know there's a matrix here. It wants you to find the rank of M and state a basis for the range space of T. Okay, this isn't actually covered that well in the mark scheme. They just sort of have this matrix and they say it turns into another one. They don't really explain how it happens, what steps you have to do. Okay, so we want to find the rank. We can add and subtract rows to each other without changing the rank or actually the determinant. And what we want to do is make the rows such that we know they're not linearly dependent. So we want to make sure that the rows are not multiples of each other. Okay, and the rank is actually rank equals maximum number of linearly independent rows. Independent rows. Okay, so what I want to do is just take a row, add it or subtract it from another one until we can be sure, so until it looks obvious that all the rows aren't multiples of each other, all the remaining ones aren't. And at this point, it doesn't quite look obvious that some of these rows aren't linearly independent. You can actually make them the same by adding and subtracting them away from each other. We want to keep the top row the same. That's normally what we do in these problems. So let's start by taking this row away from the second one. Okay, so we get a 2 minus 2. I'll just draw out the first one. Minus 1, 1, 3. So 2 minus 2 is 0. 1, we get 1 here. We get a minus 1 and we get a 2. Okay. Okay, and that's simplified things a little bit because we don't have a number here, and then we might be able to compare this to the other rows. And if we also then multiply the first row by 3 and take it away from the third row, so this I've done this one times by minus 1. I'm also going to multiply it by 3 and add it, so I'll multiply by minus 3 and add it to this one. We then also get that it gets 0, 1, minus 2, 2. So the third row is actually a linear, sorry, this should be a minus 1. It's exactly the same as the second row when we do this process. So we can see that those rows aren't independent. And we just keep doing this process, multiplying rows by -1 or 1 or -2 or -3 or something, and adding them onto other ones until we get this result, which can't be reduced any further. So we get to a matrix which is 2, minus 1, 1, 3, 0, 1, minus 2, 2, and then we just get zeros in these last ones. And so we only have 2 rows that aren't zeros, so the rank is 2. Okay? And the basis, a basis for the range space of T is any 2 independent column vectors. Okay, so we could choose this one and this one, or we could choose the first one and the fourth one, but we can't choose the middle 2. So not middle 2. Why? Because you can see the second one is just, the third one is just the second one multiplied by minus 1, so they're not linearly independent. Okay. Yeah, so sorry, just to explain what the range is. The range of a matrix is the span, which means all set of linear combinations of column vectors. So because it's a rank 2, we only need 2 of these. So that's why we could take these 2, and we had to make sure they weren't linearly independent, so not the middle 2. Okay, so just to recap. So now if we need a basis for the null space, the way we're going to do that is solve equations with 2x minus y. So solve equations with the coefficients coming from this matrix. Z, I'm going to call the third one k. So imagine we have x-axis, y-axis, z-axis, and a k-axis. We have these 2 equations just formed from the rows of the matrix. Coefficients given that way. Yeah, so if we just solve these, as you notice, we have 4 unknowns, but only 2 equations, okay? So we have 2 degrees of freedom. So we can choose maybe x and y to be whatever we like, but then that will fix z and that will fix k. Okay, so don't be confused if you can't actually find out exactly what x, y, z, and k are. That you're not supposed to be able to, but you can fix k and z. And once you fix those 2, then you then know y and x. So if you add these together, an easy way to see it is if you just add them, then you should get 2x plus 5k equals 0, which means x equals minus 5k over 2, and then using the second equation you can then get that y equals z minus 2k. Okay? So now if you choose k and you choose z, that will give you x and it will give you y. Okay, so it gives you, if you choose 2 of them, it gives you the other 2. Okay, we only need 2 column vectors for the basis, because the rank is only 2, the basis of the null space. So let's choose, we can choose whatever we want. So let's choose maybe, I think the example in the mark scheme is they take k equals 2 and z equals 0. Z equals 0. So that gives you, I'm going to write it, I'll write it down here actually. Whoops. I'll write it down here. So that'll give you -5, -4, 0 and 2. That's what happens when you choose k equals 2 and z equals 0. You need one more other one, so or you could choose maybe, the other one they choose is actually k equals 0 and z equals 1, which is a really simple one. Just gives you 0, 1, 1, 0. But you can choose anything. You can choose any of these 2 parameters, as long as you don't choose the same 2 twice, because you need 2 different vectors. So yeah, once you have these 2, or anything else, then that should form a basis for the null space of T. Okay. Right, on to the next question. Use de Moivre's theorem to show that tan 5 theta is 5t minus 10t cubed plus t to the 5 over 1 minus 10t squared plus 5t to the 4, where t is tan theta. That's the first step. So this is only worth 4 marks, but it's actually quite a lot of work. It's very tedious. The way I'm going to go about it is just by, it's exactly the same as basically the way they do the mark scheme. It's just a little different way of thinking about it. So start off by just writing the theorem that you know, de Moivre's theorem, which is that. And then if you factor out a cos theta, you get e to the I theta is, I messed that up a little bit. I don't want to write what e to the I theta again, because I don't have so much space. So yeah, cos theta 1 plus I t, where t is tan theta, but I'm using t. You want to use t for this question, because otherwise it's going to take you forever just to write it out. And there's 4 different ways really of thinking about e to the 5 theta. So you can think of just it's e to the I 5 theta, or you can think of it as it's e to the, it's cos 5 theta plus I tan 5 theta, or you can think of it as cos theta plus I sine theta to the power of 5, because it's the same as e to the I theta to the power of 5. Okay? If you just compare if you just compare this side to this side, that will end up giving you the right answer. So, sorry, that shouldn't be a tan. That should be that shouldn't be a, yeah, it should definitely be a sine. Whoopsies. I don't know if I did try and write sine, I just might mess it up a bit. Oh, that's gone a bit wrong. Cool. So yeah, that should be a sine 5 theta. So if you bring out the cos 5 theta here, you get cos 5 theta plus 1 plus tan 5 theta, I tan 5 theta. So that's if you just factor out cos 5 theta on that side. And on the other side, you're going to have a cos to the 5 theta times 1 plus I t to the 5. Okay? So once you have that, all you do is you compare the real and imaginary parts. So just think about the real part. The real part gives you the ratio of cos to the 5 theta over cos to the cos 5 theta. So that'll give you, on one side it'll be cos 5 theta equals cos to the 5 theta, and then everything in here that is an even power of I. Okay, so you get 1 plus, there'll be like an IT squared term, and there'll be an IT to the 4 term. Yeah, and you see this is the same as actually what's on the, that's the same as what's in the denominator. So there should be a 5 here from where you I forgot about all the coefficients in front of them. Yeah, so there's IT terms, there's IT to the 4 term. In front of this term, because of the expansion, there's going to be a 10. And in front of this term, because expansion, there'll be a 5. So probably the best way to do this question is just to expand this out and then look at all the even powers of I terms to get what this is. Then look at the odd powers to get what tan 5 theta. So cos 5 theta times tan 5 theta equals cosine to the 5 theta times all the odd powers, so you get like an IT to the 5 plus there would have been a 5 IT to the 4, we don't have that one, plus a 10 IT cubed, yada yada, and then you can figure out from the real part cos to the 5 theta over cos 5 theta, and after you've got that, then that should give you what tan 5 theta equals that, okay? The thing at the top. Okay? The next part of the question is completely unrelated to the previous part, just wants to know what the roots of this are, which is not too bad at all. All you need to do is just solve this equation as you would any other quadratic equation. So this t to the 4 minus 10t squared plus 5 equals 0 is the same as saying t squared minus 5. So you're just completing the squares. So you get t to the 4 minus 10t squared. You'd get a plus 25 out here, so you need to take away 25 to make it the same. Plus 5 equals 0. So you work through that, and you eventually get that t squared equals 5 plus or minus square root of 20. Okay, that's what happens when you've just worked through this equation, just treating t squared as like an x as you would in a normal polynomial question. And then once you have that, you get t equals plus or minus square root of 5 plus or minus the square root of 20. Okay, but t is tan theta. So if you just take the inverse tan of this, you take it for the only thing you really need to worry about is the plus or minus in here. Okay, so when this is a plus 5, when this is a plus square root of 20, that'll give you one answer, and then this sign change will just make the answer either be negative or positive. Okay, so I think I can't remember which way around it is. One of them gives you a pi over 5 for what theta equals, and the other one gives you a plus or minus. When this is negative, I think 2 pi over 5, or it might be the other way around. Either way, you just take the inverse tan of this to get these two numbers. So then you know the theta equals that, so therefore the roots are tan of the values. And remember, when you take tan of plus or minus something, that is just plus or minus tan of the value. Okay? Okay, cool. And then the next part is question 8. Curve C has parametric equations x equals t squared and y equals t minus t cubed over 3. And it wants you to find the arc length of C. So how do we go about that? Well, we actually use Pythagoras' theorem. So the hypotenuse is the sum of the squares. The length of the hypotenuse squared is the sum of the squares, okay? And we can actually use that to figure out the length of a differential segment, okay? So say we have, this is y-axis, this is an x-axis, we have a little arc coming along, its length dx, and it's got height dy. The actual length of that arc is going to have a d, I call it dl squared, is going to equal dx squared plus dy squared. So dl equals the square root of dx squared plus dy squared. Okay? But we don't have x in terms of y, we have x in terms of t and y in terms of t. So we can actually note that if we multiply this thing by dt, so we get a dt outside, To then make sure this still means the same thing, we need to divide by dt, bring inside the square root, so we get dt squared. So we actually get dx by dt squared plus dy by dt squared. Okay, so we can figure out the infinitesimal arc length by looking at dx by dt squared and dy by dt squared. So if you just find those out, it's 2t and y dot, where the dot just means derivative with respect to t, means 1 minus t squared. Okay, we plug those in, and you should end up integrating. So s, I called it s, sorry, I meant to call it l for length. So the integral between 0 and 1 of t squared, yeah, so dt t squared plus 1 dt, that's what you get when you square this, square that, and add them together, and then take the square root. You just do that integral, and then you should get 4/3. Okay, I think we actually end up having to do this integral, the same integral later. I think for maybe this question, I think we have to do the exact same integral. So just to point out, we have to do the same thing later. I'm not repeating myself. And now we need to find the surface area generated when it's rotated through 2 pi radians about the axis. Okay. So a way of thinking about this is that here is a y-axis, here's an x-axis, and we'll draw a curve on. Maybe it looks like that. I don't actually know. This is just a general curve. So we want to figure out the surface area of a shape when this whole thing is rotated about the x-axis. Okay. But each little, we can divide this up into loads and loads of thin little slices. I'll draw this one a bit bigger just so we can see. And when we do that, we actually note that it's a frustum, and frustrums have an area of 2 pi r L, where L is the length of this line here. Okay, it's the length of this side. And r is the radius, so r is this length. Okay. So for a little frustrum, its little area, its d area, is 2 pi, the radius, which is y, times by the length of this side. Well, we already figured that out. It's dx squared plus dy squared. Okay, so if you want to figure out the whole area, whoops. Okay, if you want to figure out the whole area, oh god, it's done it again. There we go. The whole area is going to be an integral 2 pi times the integral of y square root of y dot squared plus x dot squared times dt. Okay, just by, again, multiplying by dt over dt, so we get a dt in here. We bring a dt inside the square root, becomes dt squared, so that's how we get the x dot squareds and y dot squareds. So we can just plug in everything we need. So I'm going to put this bit up here now. So the integral we end up needing is 2 pi times once you plug in all the values, t minus t cubed over 3, which is just the y. And the other part is t squared minus 1. Sorry, plus 1. T squared plus 1 dt. And sorry, that's terribly misleading. Not working with much space here. There we go. Yeah, and once we actually compute that integral, we should get a value of, oh yeah, let me just see. Oh yeah, this integral is pretty simple. You just multiply the brackets out, so it becomes just a polynomial, and you can just integrate each term separately. And you should get an answer of 11 pi over 9 when you do this integral. Okay, cool. Right, getting near the end now. Matrix M gives you the matrix M as an eigenvector. This is just to check if you're awake, I think, this question. Once you define the eigenvalue, all you do is multiply this matrix by that eigenvector, which gives you, let me just see, 0, minus 1, 1. Oops. 0, minus 1, 1. And if you just divide, any of these terms by the original, we see that they are all minus 1 times the original, so the eigenvalue is minus 1. Okay. Now it just gives you these facts. So if you sum the eigenvalues, that gives you the sum of the trace of the matrix, which is the sum of the diagonals. And if you multiply them all together, that gives you det M, the determinant of M. So you figure out the determinant, which I just want to remind you is minus 2 times the determinant of the minor matrix, 1, 2, minus 6, minus 7, plus, and then you take this 2, so it's another minus 2, times another minor determinant, 2, 2, minus 3, minus 7. Okay, and then you also do the same for the last one, 2, so I'll just put dot, 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 do the same for the last 2. So yeah, it goes plus, minus, yada yada. So that's how you figure out determinants. Remember, this is just for the minor determinant. It's if you have A, B, C, D. Minor determinant is AD minus BC. Okay, so use that information to figure out the minor determinant, which gives you an answer of, I think, minus 12. Okay, cool. Minus 12. If you add the numbers together for this matrix, you get minus 8. And once you have those 2 bits of information, you already know that one of them is minus 1. So you can use those 2 bits of information to find out the other ones. And you should get a quadratic equation, which looks like lambda 1 squared plus 7 lambda 1 plus 12 equals 0. That's what happens when you put all the bits of information together. You get that. You solve it, you get 2 eigenvalues. One is 3, and the other is 4. That's terrible for me. Let me sort it out. Nice. Okay, so that's the, why has it done that now? So that's how you go about doing that question. Okay, so it's just pretty easy algebra. This question is actually quite nice. Okay. Use these results to find the other 2 eigenvalues. Oh, sorry, we did that. And find the corresponding eigenvectors. How do you find the eigenvectors? We'll just write out some random stream of letters, so A, B, C, maybe. Multiply M by that. And then you'll get out some some matrix. Sorry, you'll get out some. So actually, I'll just do it. I'll do it for the top rows. So if we have minus 2, 2, 2 times by this thing, we get minus 2a plus 2b plus 2c. So that's the first one. You do the other ones, and then you equate that to the original thing multiplied by an eigenvalue. So let's say 3. So it's 3a. That, and then you get a bunch of equations. You can just solve them. Okay. And then they're not specific, again, like with the previous question. Once you choose, like, for example, once you choose a value of C, that might give you the value of B and the value of A. So you just work through it and you can get any answers out, okay? So there's hundreds of, they're all multiples of each other, okay, for these eigenvectors. Cool, okay, let's move on to the next one. It is given that In equals this, where n is greater than or equal to 0, and wants you to show this. This is a bit nifty, so let's just go through the trick. So consider in plus 1, just because that's the only thing that we don't know in this equation. Or like, we know in, so if we figure out in plus 1, maybe we'll be able to figure out what the difference is pretty easily. So figure out in plus 1, well, this is going to become a 2n plus 2. So we're going to actually have a sine squared. So the integral, I'm not going to bother with the limits, just because it's messy. We get sine 2nx over cos x times sine squared dx. Okay, so you can't really take this away from that at the moment or do anything with it because of the sine squared term, but we could just rewrite sine squared as 1 minus cos squared x. Yeah, once we have that, when we multiply this by the 1, well, that just is in. Okay, so when we take in and we minus in plus 1, the 1 times that will cancel with in. So we'll just be left with the difference, and called d. It's going to equal this times by cos squared. There's cos on the bottom already. So we're going to get sine 2n x cos x dx. That'll be what the difference is. Yeah. So just to recap, we brought out the sine squared. We turned it into 1 minus cos squared. When we multiply this by the 1, we get original integral, so when we take them away, those cancel out. And then when we multiply by the cos squared, it cancels with the cos x on the bottom, so we get this. It's really easy to integrate because this cos x is the derivative of sine x. So we just integrate away, and we should get that for the difference, so in minus in plus 1, we should get 1 over 2n plus 1. So that's just add 1 to the power and then divided by the power. And then we also get 1 over square root of 2 times 2n plus 1. And with a little bit of thought, we realise that is the same answer. Minus a half, this is 2 to the power minus a half, so you get minus, and then bring the half through to get n plus a half. Okay, so these are actually the same thing. Okay, and then hence show this. It's pretty boring, this question, just because you have to work through so much stuff. So first thing to notice is that n equals 3 here, just by the exponent sign. So we can, one way of doing this, with the way they want you to do this even, is to find what I0 is, because I0 is really easy to figure out, because the sign goes away. Okay, 2 sine x to the power of 0 is 1, so we want to do an integral of 1 over cos x dx, which is in the formula booklet. It gives you the first part, ln 1 plus square root of 2. Okay, and then once we have this, we use the relation I0 minus I1 equals let me write this better. Basically, we just rearrange the formula that we're given, the reductive formula. We want to write it as in plus 1 equals in minus 2 to the minus n plus a half. There we go. Over 2n plus 1. And we want to just keep using this thing so once we've got I0, then we can then get I1. So just put n equals 0, and that gives us I1. Okay, and then once we have I1, then we can put a 1 in here. So we've got I1, then we figure out what this is with a 1 in it, and that gives us I2. We keep doing that until we get I3. Okay, and the only hard part is really adding together. You have to add together square root of 2 minus 1 over square root of 2 minus 1 over 6 square root of 2 minus 1 over 20 square root of 2, I think. Okay, so you get the first thing, and then you get minus all this, which actually, when you figure that out, it's 73 over 120 square root of 2. Okay. Okay, cool. 11. Okay, so this one's about the shortest distance between lines. Right, line L1 passes through the points A and B, which gives you. Line 2 passes through the points C and D. Okay, and it wants to find the shortest distance between the lines L1 and L2. Okay, so first thing to do is write down what are the vectors that connect A and B. So AB, it's just b minus a. So you just take every value of b and then take away a. So you get 6, 4 minus 18, I think. Sorry, minus 8. I don't know why I said 18. And then for CD, figure that out. So you just do d minus c. So 5 minus 2 minus 4. Yeah, that's right. Okay, so now that you have these are the two lines. You want to find the shortest distance. Well, one way to do that is, so these two lines sort of pointing randomly in space. But if you take the cross product, you get a line that's perpendicular to both of them. Okay, so it might look like quite hard to draw on a 2D diagram, but you get a line that's perpendicular to both of these two lines. So it doesn't necessarily have to connect them. You just know that the direction of this. All you want really is the direction. So do the cross product between these two things. You get your IJK thing, matrix 6, 4 minus a. Oh, one confusing thing about the mark scheme here is that it doesn't write 6, 4 minus 8 when it does this cross product. It writes 3, 2 minus 4. So it's everything scaled down by 2. And the reason why it does that is because it's an easy calculation, and you're not actually concerned about the magnitude of this vector. You just want to know its direction. So if you work that through, you do the cross product, and then normalize it, which is not something you do in the mark scheme, but I think it's always a good habit to get into. 2, 1, 2. That's the vector you end up with. This is a normalized unit vector, so it's a length 1 that is perpendicular to both of these vectors. Okay, now once you have a vector that's perpendicular to both of them, if you take any 2 points on these lines and create a vector, so maybe let's go AC. Is that what I did? Yeah, AC. AC is 4, 2 minus 13. Now, if I take the dot product between these two things, the modulus of the dot product, that gives me the distance between the two lines. Okay. So I don't know. Maybe the way you want to think about this is like you have two random lines, and you rotate yourself around until they're on top of each other, like this. So you just moved your head around until the lines are on top of each other. So this is the closest point. If you take the cross product between these two lines, so this is looking at it up from above. Oh, no, sorry, I'm busy. This is looking at it from above. Say this is the shortest distance between them. The vector you just figured out points in this direction. And if you take any 2 points on the line and take the dot product between this vector, that will give you this perpendicular distance, okay? So it's a bit of a thinker. If you can't really visualize it, don't worry. The formula is you just take the cross product of the two lines, you get a normalized unit vector, then you take a line joining the two lines and you take the dot product. So 4, 2 minus 13 times 2, 1, 2, third, and then just normalize. You don't need to normalize by the length of this one because it's already normalized. So you normalize by 4 squared plus 2 squared. Sorry, in fact, you don't even want to normalize by this. You don't want to normalize by anything. You want the actual length. Yeah, sorry. So you just do that. That's all you do, and that should give you 16/3, which is the answer they're looking for. Okay. Cool. Now it's doing a similar sort of thing. It's given you a plane with 3 points and then another plane with 3 points in it. So now the points, the lines AB and AD, you can figure out these vectors pretty easily. They define a plane. What I mean by define a plane is, like, say the two lines are like this, they'll be in a common plane. Okay, so yeah, so this pi, this is a capital pi by the way, this pi containing A, B and D in it means that the lines AB and the lines AD are in it as well, and they define a plane because if you take the cross product, that'll be perpendicular to both these lines, so it'll actually be normal to the plane if you take a cross product. Okay, so you want to take a cross product between these two vectors. Again, it doesn't matter. It doesn't matter about the size of the vector. You're just interested in the direction here. So I did it, and I got this. It's not normalized. I couldn't be bothered. Yeah, so this is a vector that's normal to that plane, and you do the same thing. So it's maybe AC and AD and AD. So you take the cross product of those, and you get another vector. And I got this, minus 136, minus 98, 234. So again, I figured out the vectors just by taking, like, I took the coordinates of D, took the ones from A away from it to get that vector, and then I've just done the cross product with AC to get these two vectors. Okay, and now these two vectors are the normals of the planes. So if we take the dot product between the normals, so this is like one plane normal, this is another plane normal. So one plane looks like this, the other one looks like that. Okay, so this is normal, this is normal. If we take the dot product between them, we'll actually get the angle, as long as we normalize by the height of them. So cos theta equals minus 136, dot dot dot, whatever it is, times by 4 dot 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 dot. And we normalize by the magnitudes. 136 squared dot dot dot. There's quite a lot of writing x, quite a lot of numbers involved. 4 squared dot dot dot. That'll give us cos theta, which equals 0.80228, implying that the theta equals 36.65. 36.65 degrees. Okay. Okay, cool. We've only got 2 more questions left, but I'm sort of running out of time. I want to go a little bit quicker. Actually, these are the hardest 2 questions, so maybe not. The first bit turns out to be quite easy. Okay, so once dy by dx in terms of t, we can use the chain rule. So dy by dx equals dy by dt times dx by dt, dt by dx. So x dot, which is dx by dt, is 2t, y dot is 1/2, 2 minus t, minus 1/2, and then don't forget the minus 1 multiplying by this. So we just take this one, we divide it by this one, and that should give us dy by dx. Okay, but then we want to find d2y by dx squared. So we actually need to differentiate this by y, by x again. Okay, which we can also do again using the chain rule, by dt times by dt by dx. Okay, so that's how you do it. It is just tedious maths, really, to be honest, but this is how you do it. Now it wants to find the mean value of y with respect to x over the interval 0 less than or equal to x less than or equal to 4. How do you find mean values? Let me think about the best way to explain this. So the mean value of y is a bit like finding means when you're doing statistics. You just want to do, I don't want to put a line above it because I don't want to do this, right? Because that's what some people use for the centroid coordinate. So I'm just going to put maybe, oh shit. I mean, oh dear. There we go. Oh, I don't know why that did that. Cool. Yeah. Yeah, so I'm just going to use that for the mean value. And it's exactly the same as you would figure out in stats. You just integrate over the whole region, so 0 to 4 y dx. And then you want to divide by 4 because that's like the size of the range. And you literally just plug in what y is. Dx, so if you just differentiate this, dx is 2t dt, yeah, from this. So I don't want to write it out, but you just basically do that integral. I can't remember if it's a hard integral. Oh yeah, it's not easy because 2 t 1 sorry, 2 minus t, that should be. 2 minus t to the power of a half. Yeah, so it's not an easy integral because you have this half, but again, if you just, if not again, but if you use the, if you use this, UdV, integration by parts, yeah, that's the one, don't know why I forgot that, equals UV minus, the other one, and you just, make this UU, so you make this the thing you differentiate, then, it's pretty easy to do, and that actually gives you an answer of 8 over 15 square root 2. When you do that integral. And then this one's quite weird. It wants the y-coordinate of the centroid of the region enclosed by C, the x-axis and the y-axis, okay? So let's just draw it out so you know what you're doing. It's always a good idea to draw diagrams if you get confused. So the curve, I think it looks a bit something like this. But that, that might not be right, it doesn't really matter. And so, there's a way of thinking about this. You can think it's sort of like a center of mass thing. So the area of this shape is proportional to, or you can think of it as a mass. Okay, and if you calculate that mass, just by doing the integral of y dx between 0 and 4, and multiply it by the average, that's like the turning force about the x-axis, and that should be the same. So this is like if you take the bulk shape, bulk area, and then multiply by the centroid, which is sort of like the center of mass. That should be the same as summing up all the other little bits. So it should be the same as a half 0, 4 y squared dx, which is sort of like a moment of inertia, turning it back the other way. If you can't remember that, then just remember this formula, because it's how you get the answer. We've already done this integral, well, divided by 4, so you just multiply this answer by 4 and use it. So we just need to do this integral, but then that is just a half times the integral 0 and 4 y squared, which is 2 minus t, and then dx is 2t dt, isn't it? Yeah? So once we divide by the other integral, we should get the centroid thing equaling 5 square root 2 over 16. Okay? Alright, last question. Curve C has this equation. A, B, C, and D are constants. The curve cuts the y-axis at 0 minus 2. I don't know why it bothers putting this in. If it cuts the y-axis, it has to go through 0 when x equals 0, doesn't it? Because otherwise that doesn't go through the y-axis. But anyway, I'll just draw it on. So x equals 0. Yeah, it's obviously in the y-axis. So it's quite misleading. I thought it came through the y-axis at 2 points. So maybe, but anyway, it doesn't really matter. It has asymptotes at x equals 2 and y equals x plus 1. Okay, so the x equals 2 asymptote tells you straight away this d needs to be minus 2. Because that's how you get an asymptote at x equals 2. It also wants a, b, and c. But you can find c pretty quickly because, it goes through the x-axis at y equals minus 2. Obviously, I don't know why they bother saying that. So y equals ax squared plus bx plus c over x equals x minus 2. And then y equals minus 2 when x equals 0. So 0, 0, 0 gives you c over minus 2. Implying that c equals 4. So I'm just going to draw in the constants as I fill them out. Okay, piece by piece. And then now what we want to do is we want to divide x minus 2 into this. Just in case you've forgotten how to do that, I'll go through it a little bit more explicitly. So we take the highest power we have here and divide it into the highest power there. So we've got ax. ax, and then multiply back out through. So ax squared minus 2ax. And then we then take this bit away, so these ones cancel, and then we get a b plus 2a x. And then take the highest power, divide it, so we get plus b plus 2a, b plus 2a, x, minus 2b minus 4a. We need to bring this 4 down now, because, well, we don't really, because these can't interact anyway, because this has a b in front of it and an a in front of it, but you know, that's what you normally do. Then take them away, whoops, so you should get 4 plus 2b plus 4a, okay, which means that, so you figured what this is, what x minus 2 into that is, it's ax plus b plus 2a, y equals, yeah, in the math scheme again, they don't really explain this, just sort of write down this answer. So what you're doing is you're doing division, algebraic division. Yeah, you get this plus the remainder, still divided by x minus 2, right? And you know there's an asymptote at y equals x plus 1, which means that a is 1, right? Comparing coefficients. And then b plus 2a. Yeah, because, sorry, the bigger x gets, the less and less relevant this is going to be. So this has to tend to approach x plus 1. Is that the best way of thinking about this? Yeah, the best way of thinking about this is probably, right, so you want to find what these values are, knowing that you know this asymptote. So it touches the asymptote at infinity, right? That's one way you could think about it. So when x is infinity, which isn't really possible, but anyway, this will be 0, so you need to make this bit equal x plus 1, right? So yeah, so comparing coefficients, yep, that equals 1. B plus 2a needs to equal 1, so b is minus 1. Okay, that gives you all the coefficients. Now it wants you to show that all the points on C, either y is less than this, or equal to it, or y is greater than, or equal to it. Okay, so how are we going to do this? Let's just multiply out by x minus 2, so we get xy minus 2y equals x squared minus x plus 4. Okay, is that right? Yeah, that's right, I think. Yeah. And then I'm just grouping terms. Minus y plus 1. Cool. Yeah, so I think this is the same thing. And yeah, now we have an equation. And the best way to think about this is we want x to have real roots, okay? So in order for that to happen, we need discriminant b squared minus 4ac. It's got to be greater than 0. And so for the discriminant to be, oops, oh no, yep, cool. For the discriminant to be greater than 0, we need b squared, which is y plus 1 squared minus 4ac. So 4a we don't have, and c is 2y plus 4. Yep. Okay, we work through that, and we get y squared minus 6y minus 15 greater than 0. So that's clear, it's not a 9, it's a y. Okay, and then we then work through that, and we stop here when we get y minus 3 all squared is greater than 24. Right? Let's just think about what this means. I'll put a star here so you know that, and we're just going to do it in the bottom here because I've got a bit more space. What does this mean? Most people like to do this, sorry, actually 24. Most people like to draw graphs and stuff at this point. I don't. I think the best way to think about this is, you know that you've got a number, and when you square it, it's bigger than 24. Okay? So either the number that you square, which is y minus 3, either it's bigger than the square root of 24, because then when you square it, it's going to be bigger than 24, or it's more negative. Oh, goodness. So I don't like to think of less than as a less than symbol as less than. I like to think of it as more negative. So either it's more positive than the square root of 24, or it's more negative than minus the square root of 24. That's what's going to give you an answer that makes that bigger than 24, okay? So that gives you y greater than 3 plus square root of 24, which is 2 square root of 6, I think. And then y less than 3 minus 2 square root of 6. Or equal to, because you can have the discriminant being 0, which would only give you one x value. Sorry, there are only equals here. There should always be an equals here. Discriminant could be equal to 0. Okay? I think that's all. Is that what I asked for? Y less than or equal to? Yeah. Okay, cool. So yeah, that's the best way to think about it. Okay, and that concludes the end of the paper. Thanks for watching.